Okay, so today we're going to talk about electron configurations. We touched on it a little bit yesterday, but electron configurations are your like 1s2, 2s2, 2p6, all that jazz. So you should be excited because that was easy from last year. Remember that this whole row is 3D, even though it's on row 4, 4D, 5D, 6D. And then we didn't really touch on F a whole lot last year, but 4F fits here in row 6, and 5F fits here in row 7. Alright, so they want us to write the electron configuration for the following atoms. Alright, so, and also keep in mind, remember we talked about the shorthand notation last year. Always do the full configuration unless they ask for the shorthand. Okay, and we'll do some of both. Maybe let's go here, and then we'll do the shorthand, because those are the bigger ones on the bottom. Okay, so hydrogen is in that first box. Hydrogen's electron configuration is 1s1. Lithium is the third element, so you go all through 1s and then into 2s1. Because lithium's in the first box in 2s. So 1s2, 2s1. Okay, oxygen, we go through all of 1s, all of 2s. Okay, oxygen sits in 2p, and it's in the fourth box in 2p. Over here to helium, helium is in that second box of 1s, so 1s2. Boron is in the first box, so we go through all of 1s, all of 2s, sorry. And then we go into 2p, boron's in that first box. And then neon is all the way at the end of 2p, so all through 1s and all through 2p, and then we stop. Alright, let's do the shorthand. This is called noble gas notation. So you find that element on the periodic table, you go up a row, you go all the way to the right, and you write down that noble gas in brackets. So I find sodium, I go up a row all the way to the right, I have neon, I put neon in brackets, and then I write the rest of the electron configuration, which is just 3s1. Okay, next one, find calcium, I go up a row all the way to the right, I have argon, and then I finish it, so 4s2. Phosphorus, up a row all the way to the right, I have neon, and then I have 3s2, 3p6, 3p3, my bad. Okay, remember these exponents should add up to your total number of electrons, so helium has 2 electrons, boron has 2 and 2 and 1, which is 5, 2, 4 plus 6 is 10. Okay, so your exponent should always add up to the total number of electrons. Alright, vanadium's that last one. So find vanadium, up a row, all the way to the right is argon. Okay, and then I finish 4s2, 3d3. So the next thing we're going to talk about is valence electrons. So those are the electrons that are present in the highest occupied energy level. Okay, so that outermost level. These electrons are important because they are the electrons involved in chemical reactions and basically define the chemical properties of that element. So they want us to list the valence electrons for the above elements. Okay, remember also we used to find valence electrons doing the group number. Remember that we did not do that with the transition metals though. So what you can do is you can either look at the group number for the normal ones, so the not transition metals, or you can look at the electron configuration. So when I look at the electron configuration, I go to the highest energy level and I look at how many electrons they have. So I know lithium is in group 1 and it should have 1 valence electron. I go to the highest energy level, which is level 2, and I count all the exponents. I know that lithium has 1 valence electron, same as hydrogen. Look at helium. Okay, helium, its highest energy level is level 1. It's got 2 valence electrons. Okay, that's also, helium's an exception to group 18, which typically has 8. Helium's the one that only has 2. Boron, its highest energy level is level 2. I count the exponents, 2 and 1 is 3. Okay, it's also in group 13 and has 3 valence electrons. Okay, oxygen is 6. Where else? Neon is 8. Sodium, its highest level is 3. It's got 1. Phosphorus is 5. Calcium, 2. It's also in group 2. And so vanadium. So this is one of our transition metals, so we have to look at the electron configuration. We can't look at the group number. The highest level it has is level 4, okay, and that exponent is 2. So vanadium has 2 valence electrons. Okay, so this stuff's not too terrible. Okay, so now let's talk about electron configurations of ions. So remember, ions have different numbers of electrons, okay, because they're either going to gain or lose electrons to make the ion. So they carry a net charge. So we have to pay attention to their charge when we're writing their electron configuration. Here it says if an atom loses electrons, there will be more protons, so it will have a positive charge, which means it's a cation. If atoms gain electrons, there will be more electrons than protons, so it'll have a negative charge and be an anion. So they want us to write the electron configurations for the following ions. So fluorine typically has 9 electrons, but it has a charge of -1, so now it's going to have 10 electrons. So when I write out this electron configuration, 1s2, 2s2, 2p6. Oh wait, not 6. Wait, yes, 6. Sorry. Because then it's going to have the same electron configuration as neon. Okay, strontium plus 2. Strontium typically has 38 electrons. Okay, plus 2 means it lost 2, so now it has 36. Alright, and then we're going to do the shorthand for this one, because this one's kind of long. So this should be argon, and it's going to be 4s2, 3d10, 4p6. Okay, so let's talk about something too. This strontium ion has the same electron configuration as krypton. Okay, when it has the same electron configuration as another element, we call those two things isoelectronic. Okay, iso means same. Okay, and it's got the same electronic, oh gosh. I cannot spell today, electronic. Okay, so what I would say is that the fluorine ion, so fluoride, is isoelectronic to neon. The strontium ion is isoelectronic to krypton. That's how I would say that. So it just means that you have the same number of electrons. Alright, so now it says transition metals, ions. Remember, their valence electrons are the electrons involved in reactions. Good Lord. In transition metals, the electrons are the electrons that are lost, not the highest energy electrons. But we look at that level to figure out what our valence electrons are. Okay, so now they want us to write the electron configuration for iron plus 2. So if I have that, plus 2 means that I lose 2 electrons, okay, because it's plus 2. All right, and just to start, let's do the uncharged first. Okay, so we'll just do the shorthand. So it'd be argon, and then it would be 4s2, 3d6. All right, so what happens here is that when it does lose electrons, it's going to lose the outermost first, okay, because those are our valence electrons. Level 4 is the highest energy level that we have. So when we write the electron configuration for iron +2, it will still be argon, but it's going to lose these two because those are in the highest energy level. So it'll just be argon and 3d6. Okay. We do have exceptions to writing electron configurations. Just like everything we do in chemistry, I feel like there's always an exception. So this we've talked about before. We're always going to explain this in terms of areal. Okay, so that's attraction, repulsion. This is just the divider. And then energy levels is E and L. All right, so exceptions to writing electron configurations. It's important to remember that these exceptions apply only to transition elements. For certain reasons, there's a special stableness associated with both half-filled orbitals and filled orbitals. This means that the electron configurations of all the elements in the columns containing the elements copper and chromium do not fill as expected. So I think we did this one last year. Okay, so again, these are our exceptions. They want us to write the electron configuration. This is kind of bunched up. For copper, as you would expect. So if I do that, so argon and then 4s2, 3d9. I'm going to go ahead and write chromiums also, argon, and then we have, let's see, 4s2, 3d4. Okay, so again, this is copper as you would expect, but there's a certain exception that goes to this. So keep in mind the S and D orbital are close in energy. That's why they're right next to each other. Okay, so what this actually looks like, here I'm going to write it in a different color, blue. So we have argon, and what's actually going to happen is 4s1, 3d10. Okay, and this is for all of the copper family. So it's from S to D only. It doesn't happen with P at all. And again, this is what all of the copper family looks like. And basically what's wanting to happen is that it's wanting to fill that D orbital. Okay, because technically the D orbital is closer because it's the third energy level. So I'm just going to draw out 4, 5, 6, 7, 8, 9. So it's really wanting to fill this. Again, this 3D is closer to the nucleus than 4S. So then it's going to be more likely to fill that 3D fully and completely than leave 4S just with one electron because it's farther away, so the attraction's not as great. So again, we're explaining all this in terms of areal. All right, so again, that's for all of the copper family. Now let's look at chromium. We've done our expected. So what actually happens here is that, let me do it in blue again. We're going to have argon, 4s1, and now this is going to be 3d5 to kind of stabilize that D orbital. Again, 4s is farther away than 3d, so we're okay with leaving this guy alone, that electron. And this is for all of the chromium family, so that entire group. Oops, family. Okay, we also have in this situation, I'll write it in black, we have an electron repulsion in the 4s. Okay, because it's only got 2 electrons. So the thing about the 4s is that when you have 3d4 or 3d9, the repulsion that's happening in 4s actually has somewhere for that electron to go. So it goes and jumps to 3d both times. So we have the attraction to the nucleus playing a part because 4 is farther away, and then we have this electron repulsion that's happening in the 4s. If you try to take an S, like an electron from the S and place it in the P, those two are like really far apart, so it's kind of like jumping the Grand Canyon, and we don't do that. Okay, so S to D is okay, S to P, not okay. Okay, now we're moving on to orbital spin diagrams. So we did those. This is where you actually draw out the electrons. So let's take a look here. You do need to know the difference between an orbital diagram, which is what we're about to do, and the electron configurations, which is what we just did. So here is oxygen. These boxes are kind of all over the place, so I'm just going to do my own. And then I'm going to put my electrons in there. All right, so 1s2, 2s2, 2p. So remember, I got to put 1 in every box before I can put a second. So I fill all of 1s before I move to 2s. I fill all of 2s before I move to 2p. I put 1 on every line before I put a second. Okay, so, and that actually has a name for that, by the way. It's called Hund's rule. Okay, we didn't really learn the names of rules last year. I just kind of told you the rules. That just says that there has to be 1 electron before you put 2. All right, now they want us to draw the spin diagrams for the following atoms. So we're going to do nitrogen first. Okay, you can do a shortcut with them. You can do the noble gas notation. And then we just draw out the rest. So this is 2s and this is 2p. Okay, nitrogen is 2p3. All right, and then over here we can do manganese, so we'll go up 1 all the way to the right. I've got argon, and I've got 4s and 3d. Okay, so this is something we haven't talked about before. Diamagnetic and paramagnetic. Okay, if something is diamagnetic, it's an element that has no unpaired electrons, and we draw out the orbital diagram. And then an element is said to be paramagnetic if it does have unpaired electrons. So a lot of your elements are probably going to be paramagnetic. So para, by the way, means unpaired. All right, now this question is asking which of the following elements are diamagnetic, which ones are paramagnetic. So kind of think of it too. Di means 2. Oops, di means 2, which is like being paired together. Ooh. Yikes. Okay, so I'm just going to write the end of these. So magnesium ends in 3s2. Okay, so that means that it is diamagnetic because it is paired off. Okay, I don't have any unpaired electrons when I draw out that entire diagram. Down here I've got iron. Iron ends in 4s2, 3d6. Okay, so 6 means I do have some unpaired electrons because it can hold 10 in the d orbital, so this is going to be paramagnetic. Okay, over here to cadmium. Cadmium 4s2, 3d10. Okay, everything's all paired up, so this is diamagnetic. Phosphorus ends in 3s2, 3p3. Okay, so I've got these 3 unpaired electrons, which is paramagnetic. Okay, so not too bad of a concept. All right, last page. This is something we did not talk about last year. So this is talking about electrons in their excited states. So it says electrons in their lowest energy electron configuration are said to be in their ground state. When electrons are in the ground state, they usually obey 3 rules governing electron configurations. Here, first we have the Aufbau principle. Aufbau means to build in German. Okay, and all it says is electrons enter orbitals of the lowest energy first. Okay, so you're building up to a higher energy level. Okay, next we've got Hund's rule. It says that electrons enter orbitals of equal energy one at a time with parallel spins. Okay, so that's where I put one in every box before I put two, and then, one has to point up and one has to point down. So here I'm going to draw a couple examples. So if I was, actually let me put it in black. If I was in the ground state, it would look something like this. So I put one in every box. They're all going to point up because the other ones would point down if they continue to get filled. Okay, if I did have an excited electron, it could violate this rule. Maybe my spin got all funky. Okay, so this spin is off. It's pointing the wrong way. So that's a way that you can tell that something got excited. So also what happens too, the reason we're talking about these is that you can excite electrons and then they jump to a higher energy level. Okay. All right, there is one rule that you cannot violate, and that is the Pauli exclusion principle. Okay, no two electrons in the same atom can have the same 4 quantum numbers. Okay, so the quantum numbers are like your energy level is N, your sublevel is also represented by N. So remember your sublevels are S, P, D, and F. Then you can go on to orbitals. That has its own quantum number. I don't need you to know that, but it does. And then total electrons is another quantum number that that has a letter that represents it, but we don't need to know that right now. So again, this is one that you cannot violate. Okay, so basically what it means is you can't have 2 electrons in an orbital that look like that. This is a no-no, okay, because these 2 electrons right here would have the same energy level, which is, I told you, is its own quantum number. It would have the same orbital, which is another quantum number, and the same electron. Okay, those are all their own quantum numbers, and you can't have 2 electrons with the same 4 quantum numbers. All right, last little bit. When electrons in the ground state absorb energy, they change their configuration to the excited state. So that's kind of what we talked about over here. This means that either the off-bow principle or Hund's rule is violated. Okay, but those are the only 2 that can get violated. Pauli exclusion principle can never be violated. Any violation of this rule is impossible. For each of the following, we need to decide basically what state it's in. If it's violating a rule, we need to figure that out. So let's look at this first one. All right, this one doesn't look like anything's wrong with it. So this is a ground state configuration, and there's no violation. Okay, this next one, I've got this little guy who's pointing the wrong way, so I know that this is an excited state because it's violating Hund's rule. Okay, remember Hund's rule, you have to enter orbitals one at a time with parallel spins. So this one got a little funky with its spin, therefore it violated Hund's rule. Okay, next one. Here I've got 2 electrons pointing up. I can't do that, so this is not possible. This is violating the Pauli exclusion principle. All right, next one. Good. Ooh, got another guy pointing the wrong way again. This is an excited electron, which is violating Hund's rule again. All right, next one. Okay, we're good. These 2 are pointing down. So again, this is another one, not possible. It's violating the Pauli exclusion principle. Okay, next. Okay, so, I mean, we could call this 4s and 3d5. This is 4s1. Here, this is the electron repulsion that took place, and it kicked that electron out of 4s into 3d to make it have 3d5. So this looks like something from the chromium family, which is okay. So this is a ground state electron configuration. No violation here. So again, this is A-okay. I know this is could be 3D or anything in that 3D5 family, like the chromium family, because I got all these blanks. Okay, so 5 blanks with this 1 blank, which I know is an S. Okay, obviously something got kicked out of 4S and popped over here. Not necessarily right there. There. Alright, last one. This is actually a P and an S. Okay, and I've got 2, 4, 6, but remember I can't kick out of S and go to P. That can't happen. So that means that I'm missing an electron. So that means it got excited somewhere, and this violated the off-bound principle, which is the building principle. All right, that's it for today.